In today's video, I wanted to go over how we find the gravitational potential energy function now that we're dealing with much larger distances. So you might think, well, I already know what the gravitational potential energy function is. It's just mgh. The problem is that we use that for h's or heights that were relatively close to the surface of the Earth. And what's really important in that expression is that the acceleration of gravity, g, was assumed to always be 9.8. But as we see in this chapter, as we learn more about gravity, the acceleration of gravity will all actually decrease as we get very large distances away from the Earth. So as we go out into the atmosphere, the acceleration of gravity decreases, just as the force of gravity does as well. So this expression doesn't work for us in the context that we're looking at this point. So we have to go back to the drawing board. So our scenario is we're imagining going from one orbit around the Earth to another. The first orbit being at a distance of r1 and the second one being a distance of r2. The path that we're taking from R1 to R2 is shown by the pink line. Now, something that's important to understand is that what we want to do in order to find the potential energy function is related to the work done by gravity. So just to remind you from previous chapters when we learned about potential energy, we said that the change in potential energy was equal to minus the work done by that force. So remember, potential energy is always related to a specific force. And so if we calculated the work done by that force, the negative of that work would give us the change in the potential energy. So our force, of course, right now, is the force of gravity. Now, as we think about that, remember the force of gravity that we learned about is radial. It only depends on the distance between 2 points and is always along that radial direction. So when we think about the work that gravity is going to do, there's only going to be work done in this little portion of the path. There's no work done here because of the fact that the displacement and the force of gravity along that piece of the path are going to be perpendicular to each other. So we're only going to do work here as we go out from R1 to R2. So setting that up, we have the change in potential energy is equal to minus the work done by gravity, which is minus the integral of the force of gravity dotted with the displacement. Now, what I found so far is it's only going to matter when we move in the radial direction, so it is just dr. But another thing that I want to call attention to, because we have to be careful here about our signs, it's minus the work done. But think about the fact that as I'm going from this point right here to this point right here, my displacement is outward, but my force of gravity is inward. So the work that gravity is going to do is negative in itself. And so what's going to happen is we're going to actually end up with a positive sign because the work is negative and we're taking minus the work. So this is going to end up to be equal to the force of gravity. We're just going to let that as unknown mass, the mass of the Earth. And then we're integrating dr over r squared. So the r squared comes from the force of gravity expression. These terms I took out front because they're just constants, and we're going to integrate from R1 to R2. Now I want to talk about the signs one more time because I know it can be confusing. It kind of makes your head hurt when you start thinking about it too hard. The change in potential energy is minus the work done by gravity, but in our scenario, gravity is doing negative work. So I have minus a minus, and that's why now this is a plus. It's kind of important. Now, when I integrate this, well, first of all, I'm going to just rewrite delta U. And I have big G, M, M, E. And then the integral of 1 over r squared is just minus 1 over r, and I'm going to evaluate it at r1 and r2. And so now that's going to give me minus g me over r2, and then I'm subtracting that evaluated at r1, but it's negative, so I'm going to have another minus, a minus, and so altogether my change in potential energy is equal to minus big G me over R2 plus big G me over R1. So, this isn't really showing up that well, so let me just kind of write over it really quickly. And sorry about the squeaking. Okay, so my change in potential energy, of course, is U2 minus U1, the potential energy it had at point 2 minus the potential energy it had at point 1. And so if we compare that, we actually could infer what the potential energy, just plain old U, is, and we end up with this result, that U is equal to minus big G me over R. So one of the reasons I really belabored the units is because we want the, not the units, the sign is because we need the sign to come out correctly. I mean, obviously I want to get the right answer when I do this derivation. It turns out that our potential energy function for gravity is actually negative. It's a negative quantity. It's going to be most negative, of course, when R is small, but as R increases, the value of the potential energy is going to get bigger, but the reason that it does is because it becomes less negative. Now, the negative sign actually means something in physics. The negative sign is reflective of the fact that we are talking about a potential energy function that is related to an attractive force. I had mentioned that when we talked about gravity on Monday, that gravity is a force of attraction between two objects. And the reason that that potential energy function is negative, it has a physical meaning. And it is because of the fact that it's related to a force of attraction. We're going to see something similar second semester when we look at the force between charges, but that's a little bit more involved because sometimes they attract and sometimes they repel. Depends what the sign of the charges are. In any case, this is our new potential energy function for gravity. It allows for the fact that the acceleration of gravity is going to be changing as we move at different distances away from our central object, which in this case was the Earth. I also want to mention that while we used MGH and we said you can say U is 0 wherever you want, this form of this potential energy function actually requires that we have a distinct point where the potential energy is 0, and that is at infinity, which you could see that it's going to turn out to be 0 at infinity. So that is always going to be our reference point. Another interesting thing that we can think about is that this potential energy function at some distance of separation r can also be thought of the work that would be done by an external force. Now that's not gravity, it's a force other than gravity. If I took these two objects and took them from an infinite separation and brought them into that present separation of r. Notice that if I said that, I said that that potential, this would be equal to the work done by that external force, and it is a negative quantity, and that is because that the objects would tend to come together spontaneously because of the attraction. So I know I've given you a lot to think about, You might want to watch this video more than once to make sure that you get all the important points because there's a lot of them. All right, that's it for this one. Bye.